Good day everyone, welcome to Bright Engineering. Today we are going to find the inverse Laplace of a differential equation. So most of the time we just get functions and then we are asked to find inverse Laplace, or we are asked to just change the differential equations into like any function that we are supposed to change it into, right? But in this time around we are going to change it into a function and then we find the inverse Laplace of that function too as well. So interestingly, when we are changing a differential equation to a function, or you want to change it into the Laplace form in terms of s, what we are most particular about is the squares that is attached to the differentials that we are using, right? So whenever you see dy ds or dy dt, it means that we are talking about the s in terms of s, right? So the power of the dy is the one that's going to attach to the s. So this side we have d squared y over dt squared. So here we know that there's definitely going to be a s, and then we attach the power to it, so s squared. But then this is the differential form of y of t. So it means that if we have to change y of t to Laplace, we are going to get capital Y of s like this, and here plus 12 is a constant, so we bring our 12, and because this is a differentiated form, we know that we are going to get our s. Since it doesn't have any power, we are not going to bring any power here, but then it's y of t that has been differentiated in this form, so we are also going to get y of s for this one, plus 32, which is a constant, and because there is a y, we are also going to get y of s for this part, is equal to 32u over t. So ideally you can say that because it's u over t, you should write 32 capital U of s, but then this is in Laplace, this stands for a unit step function. So for unit step function, if you are changing it to Laplace, you are just going to get 32 over s, because a unit step is just 1 over s. So you multiply this 32 by the 1 over s, and then we are getting this. So here we can see that y of s is common to all of them. So we can bring y of s out, we get our s squared plus 12s plus 32, and it will give us 32 over s. Now we want to find the function itself, which is the y of s. So now we make y of s stand alone, and we are getting y of s equals to 32 over s, and this will go down here, so s will be multiplying x squared plus 12x plus 32. Now, since we are done finding our function, we have to find the inverse Laplace of this differential equation or this function. And in order to do that, we have to use our partial differential equation to break this down so that we would get a similar or an easier form of the inverse Laplace, and changing it won't be a problem. So in view of that, we can just punch this into our calculators to get the root of this. And when we punch this into our calculator, our root is going to give us s plus 4 and s plus 8. So we can say that y of s is equal to 32 over s into bracket s plus 4 and into bracket s plus 8, right? And when we have something like that, we have three different denominators multiplying, so it means that what we are going to get is three different constants. So this we can equate it to k1 of s plus k2 of s plus 4 plus k3 of s plus 8. There is no, what do we call it, it's not by force that you should use k. You can use a, b, c, you can use any variable that you feel comfortable, so far as it's a variable, and then we are looking for those three different constants, right? So now we can equate this to this. So when we equate this to this, we have to find an LCM for this and get a common denominator for this as well. So we are going to get 32 over s into bracket s plus 4 s plus 8 is equal to, so finding a common denominator for this, we are going to get s plus 4 and s plus 8, because we are just going to multiply all the three of them, right? So now s will go into these ones, so these two will multiply the k plus 1, so we have k plus 1 s plus 4 s plus 8. The same thing applies to this, so s4 will go into this, and we'll take away this, so we multiply it by s and then s plus 8, get plus k2 s plus 8, and the same thing applies to the k3, so plus k3, taking away s8, we get s plus 4, like that. Since the denominators are the same, we can just equate the numerators to each other. So now we are getting 32 is equal to k1 s plus 4 s plus 8 plus k2 s plus 8, and then there is an s, and plus k3 s plus 4, and also there is an s. So now we are finding these three constants. In order to do that, we have to make sure that they stand alone. So now we are going to pick up random variables of s that will make each of these constants to stand alone. So first of all, we are going to deal with when s is equal to 0, because when s is equal to 0, this will go away and this will also go away, but then we can find k1. So when s is equal to 0, we are getting 32 is equal to k1 into brackets. Because here is going to be 0, we are going to get just 4, and this one will go to 0, so we are getting just 8, right? So we are getting 32, 8, 4 times 8, which is 32. So 32 k1 is equal to 32, and when we divide, we are going to get k1 to be 1. Now, to find the second term, if we want to make this go away, or k3 go away, or k1 go away, then we have to use s is equal to -4 or -8. So let's start with -4. So when s is equal to -4, means that k1 will go away, because this one will turn to 0 and this whole expression will go to 0. This one will also go to 0, this whole expression will go to 0. So we are left with the k2. So we are getting 32 is equal to k2 into brackets -4 plus 8 multiplied by, don't forget this s, -4, right? So -4 plus 8 is going to give us +4, but +4 times -4 is going to give us -16. So you're getting -16, k2 is equal to 32, right? And we are going to get k2 to be equal to -2. Now we have to find the last expression, which is k3. So for k3, just like we did with the first and second one, we have to make sure that it's the other expressions 1 and 2 goes to 0, and then the common term they have is 8. So when s is equal to -8, this will go to 0, this will go to 0, we are left with this. So we are going to get 32 is equal to k3 into brackets -8 plus 4 times -8, like this. This plus this will give us -4. -4 times -8 is going to give us +32. So we are also left with 32. K3 is equal to 32. So K3 is going to give us 1. So now we know that K1 is 1, K2 is -2, and K3 is equal to 1, right? So now we go back to our original equation, this form. So we are going to insert it into this. So now we are going to get 1 over s plus this k2, which is the -2 over s plus 4 plus k3 is also 1, so 1 over s plus 8, right? And then now we can change this form into the Laplace that we want, right? So changing this form to Laplace, like I said earlier, when you want to change your unit step to Laplace, it's just 1 over s. So when you want to inverse it or turn it back, it means that you are going to get the same unit form, right? So here, interestingly, our y of s is now giving us 1 over s. This negative will affect this, so -2 over s plus 4 plus 1 over s plus 8. So going through our inverse Laplace, this would give us inverse Laplace of y of s is equal to inverse Laplace of 1 over s minus 2 over s plus 4 plus 1 over s plus 8, like this. And here we are going to get y of t, because this will also reverse, and here we are going to get just 1 minus, this is a constant, so we can bring the 2 out. And then for inverse Laplace, when you have 1 over s plus 4, it's just the same as writing e and then negating what you have at the denominator here, which is the -4, and then you bring your t, because they are functions of time, right? So the same thing applies to this side. So you are going to get e, find the negative of this, which is the -8, and then attach your t, right? And then please don't forget your unit step, because they are all unit step, because they are 1 over something, 1 over something. When you bring this constant out, you're getting 1 over something. That's why you are bringing this unit step out, right? So thank you very much for watching this video, and don't forget to comment, like, and then share.